All right, everyone get ready, because today we're going deep into the world of quantum mechanics.
Oh,
We're
yeah.
going to be talking about the math behind it all.
The math, that's the good stuff.
It is, and we've got this essay by Jorgo Schneppat to help us out.
Schneppat. I like this guy.
It's called Mathematische Grundlagen der Quantenmechanik verständlich.
Wow, that's a mouthful.
It is, but basically it means uh, understanding the mathematical foundations of quantum mechanics.
Okay, so we're talking about the real nitty-gritty of how quantum mechanics works.
Exactly.
That's exciting.
So Schneppat really jumps right into it,
Oh, yeah.
He says, forget everything you know from classical physics.
Like, throw out the rule book.
Exactly.
Okay, I'm listening.
Because in the quantum world, it's all about probabilities.
Probabilities, not like concrete certainties.
Nope, you're not going to find things in a definite place.
Whoa. Okay, so how do we even describe things then?
Well, Schneppat says we have to use different tools,
Like what?
like vectors in Hilbert space.
Hilbert space. Now that sounds like something out of Star Trek.
Kind of. It's like a mathematical space where we can describe all the possibilities of a quantum system.
So instead of saying a particle is here, we say it has a certain probability of being here.
Exactly. And it could also have a probability of being somewhere else at the same time.
Mind blown.
Right. And that's where these wave functions come in.
Wave functions, what do those do?
They describe the probabilities, like a map of where the particle might be.
Okay, so it's like a probability cloud, not a pinpoint location.
Exactly. And then to figure out how these probabilities change over time.
Yeah, because things aren't just static, right?
Right. We need something called the Schrödinger equation.
Ah, the famous Schrödinger equation. I've heard of that one.
Yeah. And Schneppat calls it a cornerstone of quantum mechanics.
Makes sense. It's got to be important if it has a whole equation named after it.
It is. And to help us understand it.
Because I'm guessing it's not the easiest thing to wrap your head around.
Not really. He uses this example of a particle trapped in a box.
A box. Okay, I can picture that.
So imagine this particle.
Okay, I'm picturing it.
It can't just be anywhere inside the box.
Ooh.
It can only exist at specific energy levels.
Hold on, specific energy levels, like it can only be on certain, shelves or something inside the box.
Kind of. It's like it can only be on certain steps of a staircase.
So not like a smooth ramp, but more like...
Yeah, like it has to jump between these discrete levels.
That is weird.
Right. It's called quantization.
Quantization, so instead of being anywhere at once, it's like restricted to these certain spots.
Exactly, and that's one of the key differences between quantum mechanics and classical physics.
So with the Schrödinger equation, we can figure out the probability of finding the particle on each of these energy levels, right?
Right, but then Schneppat throws another curveball at us.
Oh no, what is it now?
Fourier transforms.
Fourier transforms.
Yep, he says they're like having two different lenses to look at the same quantum object.
Two lenses? What do you mean?
Like one lens shows you the particle's position,
Okay, that makes sense.
and the other lens shows you its momentum.
So it's like we need a whole different perspective to see this thing clearly.
Exactly, but here's the catch. You can't use both lenses at the same time.
Wait, what? Why not?
That's where the Heisenberg uncertainty principle comes in.
Okay, this is where it gets really interesting.
So the more precisely you know the particle's position,
Yeah.
the less you know about its momentum, and vice versa.
So it's like a trade-off. The more you focus on one, the blurrier the other gets.
Exactly. And Schneppat says this isn't just a limit of our instruments.
It's not.
No, it's a fundamental law of nature.
Wow, so we're not just talking about limitations in our ability to measure.
Nope, it's like the universe is saying you can't know everything with perfect certainty.
That's kind of a humbling thought, isn't it?
It is, and it makes you realize just how mind-bending quantum mechanics really is.
Okay, so we've got Hilbert space, wave functions, the Schrödinger equation, Fourier transforms, the Heisenberg uncertainty principle.
And this is just the tip of the iceberg.
So we've got a lot more to unpack here.
We do, but I think we've laid a pretty good foundation so far.
I think so too.
And it's all thanks to Jorgo Schneppat and his amazing essay.
This guy, he really knows his stuff.
He does, and he's made it so much easier to understand the
crazy world of quantum mechanics.
Yeah.
I'm excited to see where this goes.
Me too, and I'm sure our listeners are as well. So it's like all this crazy math actually has real-world applications.
Oh, yeah. Big time.
It's not just some theoretical thing.
Nope. It's the backbone of a lot of the technology we use every day.
Exactly. Schneppat even talks about how lasers and transistors.
Medical imaging, too, right?
Yeah, all that stems from quantum mechanics.
And, Schneppat makes a good point. This didn't happen overnight.
It was a process.
Yeah, like a journey of discovery with all these brilliant minds.
Bouncing ideas off each other, sometimes clashing.
Oh, there were some epic battles in the history of quantum mechanics,
For sure. And Schnepp mentioned some of the key players.
starting with Max Planck.
The OG quantum guy.
Planck really got the ball rolling with his idea of quantized energy.
Those little packets of energy, right?
Yeah, but you know what's funny? Schnepp says that even Planck himself wasn't totally comfortable with his own theory at first.
What? Why not?
Well, it seems like he saw it more as a mathematical trick to make the equations work.
Not like a true description of reality.
Exactly, and Schnepp points out that it took someone like Einstein, who was more of a radical thinker.
To really run with the idea of quantized energy.
And you know, Einstein used it to explain the photoelectric effect.
Yeah, that's where light shines on a metal and knocks electrons loose.
Which is pretty wild when you think about it.
It is, and Schnepp highlights how Einstein's work.
Along with Niels Bohr's model of the atom.
Ah, yes, Bohr and his electron orbits.
Little planets around the sun.
But even that model, as revolutionary as it was later refined.
Schnepp reminds us that science is always evolving.
Always getting closer to a more complete picture of reality.
And, you know, there's some major disagreements along the way.
Like the famous Bohr-Einstein debates.
Oh, yeah, those were legendary.
Like two titans of physics going head to head.
Schnepp actually quotes Einstein saying, "God does not play dice."
I love that quote.
Because Einstein really believed there had to be a deeper explanation for the randomness in quantum mechanics.
But Bohr, he was like, nope, we gotta embrace the weirdness.
Embrace the uncertainty.
As a fundamental aspect of the universe.
And Schnepp emphasizes how these debates, even though they were philosophical,
They really pushed the field forward.
and they all stemmed from those mathematical tools we were talking about earlier.
It's like, without the math, you couldn't even have those arguments.
So these pioneers of quantum mechanics, they really shaped the course of history.
And Schnepp does a great job of bringing their personalities to life.
He shows that science is a human endeavor full of passion, debate, and sometimes
Stubbornness.
exactly.
But it's, Schnepp doesn't just dwell on the past.
He talks about some of the exciting new developments.
Like quantum computing.
Oh, yeah, that's mind-blowing stuff.
So instead of bits, which are either 0 or 1, we have qubits.
Which can be both 0 and 1 at the same time.
Like the ultimate multitaskers.
And Schnepp explains how this allows quantum computers to solve problems that would take classical computers.
Like forever.
Yeah, it's like comparing a snail to a spaceship.
And he talks about how quantum computers could revolutionize all sorts of fields.
Medicine, material science, artificial intelligence.
And then there's quantum cryptography.
Oh yeah, using quantum mechanics to create unbreakable codes.
That's straight out of a spy movie.
Oh, I know, right?
But Schnepp makes it clear, this is all very real.
It's not science fiction, it's happening now.
It's all based on these fundamental principles of quantum mechanics.
Which Schnepp has done such a good job of explaining.
I feel like I'm starting to get a handle on this stuff.
Me too, it's definitely a challenge.
But it's a fascinating challenge.
Absolutely, and I think that's what Schnepp wants us to take away from his essay.
Yeah. That sense of wonder and curiosity about the quantum world.
And the potential it holds for the future.
It's like he's opened a door to a whole new universe.
And now it's up to us to explore it.
I'm ready to see what's behind that door.
Me too, let's go.
It's amazing to think something abstract as quantum mechanics
Oh yeah.
actually has such a big impact on our lives.
Schnepp, he really drives that point home.
Totally. And he talks about how all those theoretical concepts,
The ones that seem so out there.
yeah, they often lead to these amazing breakthroughs.
It's like the foundation for so much of the technology we have today.
It really makes you appreciate the importance of supporting scientific research.
Even if we don't see the practical applications right away.
Exactly, because you never know what those explorations might lead to.
Schnepp essay has definitely opened my eyes to the potential of the quantum world.
So as we wrap up our deep dive into Schnepp essay,
What are some key takeaways for our listeners?
well, I think the biggest one is that quantum mechanics,
Even though it seems so complex,
right, and counterintuitive.
it is understandable.
Schnepp has done a great job demystifying the math.
Showing how these tools can help us understand the universe at its most fundamental level.
And it's empowering to realize that we can access this knowledge.
We don't have to be physicists to appreciate the beauty of it all.
Schnepp's essay has given us a glimpse into this fascinating world.
And it makes you want to learn more.
I know I do.
That's the beauty of it. This is just a starting point.
There's a whole universe of knowledge out there waiting to be discovered.
Who knows? Maybe one of our listeners will make the next big breakthrough in quantum mechanics.
That would be amazing.
So keep questioning, keep learning.
And never stop exploring.
Well said.
Thanks for joining us on this deep dive into the mathematical foundations of quantum mechanics.
With Yurgo Schneepat as our guide.
It's been a wild ride.
And remember, this is just the beginning of your quantum journey.
Until next time, keep exploring.